everybody. Thank you for coming. I'm Emanuele Naccini, chair of the Oakland Structural Group. Welcome to this new event, an improved method for cold form steel beam column design. Our speaker today is Mariam Hassanali, and Dr. Mariam Hassanali is a structural research engineer at HERA, and she works on focusing on developing innovative design solutions for the metal industry, and also she brings a decade of research and consulting experience across New Zealand and Iran, specializing on seismic design, analysis, and assessment of the various structural systems. And her PhD at the University of Auckland focused on structure, behavior, and design of cold form steel components subject to combined gravity and lateral loads. And so please welcome our guest speaker. And thank you.
Okay, hello everyone. It's a great pleasure for me to welcome you all to today's presentation on improved method for cold form steel beam column design. In today's presentation, I'll walk you through three key areas. At the beginning, we will have an introduction on the cold form steel design, what are they and how they are designed. And then I'll focus on my PhD project, which was on the design of the beam columns, which are structural components that are subjected to the combined actions of the axial compression and bending moments. And lastly, I'll wrap up by briefly sharing about what we are doing at HERA. Cold form steel structures brings a couple of advantages like lightweight that makes them easy to handle and also reduces the structural demands, and their fabrication provides high dimensional accuracy. Their computer control and construction manufacturing ensures their precision. Ability to recycle can support their sustainability, and also because they are portable, they are actually suitable option for remote area and mountainous areas, and ease of transportation that makes them quite suitable option for high speed in the construction. Cold form steel structures, cold form steel components can be used in both structural and non-structural components. If we, on the structural side, they are ideal for low to medium rise buildings when the speed and the lightweight is necessary, and they are suitable for the portal frames, ideal for single to low rise industrial buildings, warehouses, and commercial. And they are also necessary for the rack systems, for the logistic and storage facilities when the high strength to weight ratio is necessary. On the non-structural side, they are quite common in partitions and ceilings, cladding support, and service and utility supports, for example, for the piping tray and actually for the electrical pipes. Because the building design will be more interesting for you, I just want to mention to the different lateral force resisting systems that can provide the safety of the building against the earthquake load. This system, one of the lateral force resisting system is the sheeting walls that can use materials like gypsum boards, cement particle boards, or timber and plywood that can provide shear stiffness. On the brace sides, we have strap brace walls and K-brace walls that are diagonal members that can direct the loads to the foundation. We also have hybrid system that the cold form steel can combine with the reinforced concrete or heavy steel. And lastly, we have moment resisting systems that the connection of this system can provide enough lateral restraining against the lateral loads without needing any other system like sheeting walls or brace walls. About the design specifications based on the regions, I just mentioned a couple of them. For example, Australia and New Zealand design standard 4600, which is quite common in New Zealand and a standard and can be used for structural and non-structural components. In New Zealand, we have NASH standard as well as the bulletins of the brands to support the design of these structural and non-structural components. In the North America, one of actually the most well-known design standard is the AISI. And in the Europe, Eurocode 3 parts 1 to 3 are common for the design of these systems. Low buckling resistance of the cold form steel limit their strength and ductility, so these members may have limitations on the high loading, high applied loads. There are three kinds of buckling. On the cross-sectional buckling, we have local buckling and distortional buckling. These kinds of buckling just happens on the parts of the cross-section. And the local ones involve plate flexure and bending. Actually, the deformed shape happens on the web or flange of the cross-section, and these kinds of buckling has the lowest half wavelength and happens earlier than other buckling modes. And the other cross-sectional deformation buckling is distortional buckling. This buckling involves the out-of-plane deformations, involve distortion of the cross-section and torsion, and it actually involves the deformation of the fault lines when the plates actually cross together, web and flange, or the lips of the cross-section, and the half wavelength is longer than the buckling, of the local buckling, but shorter than the global buckling pattern. On the right side, you can see a couple of visualization of the local and cross-section and distortional buckling. On the top, you can see the distortional, and you can observe the deformation on the fault lines that is happen in the between the flange and web. And on the bottom, we have local buckling that happens mostly on the plate, web, and also on the flanges. They are obtained from the finite element analysis. We also have another buckling, which is called global buckling, and it happens on the entire cross-section without just deforming local parts of the cross-section. We have flexural buckling. In this buckling, the cross-section deforms out of plane, and it mostly happens around the wick axis, and it has the longest half wavelength. Next, we have torsional buckling, and that section rotates around its longitudinal axis due to the torsion load. And lastly, we have a combination of the flexural and torsional buckling. Some examples are provided on the right side, and you can observe them. And about the design of these elements, we have two design methods in the world. Effective width method, which is actually the one that Eurocode just specified. And we also have direct strength method that is most common in Australia, New Zealand, and the US. Effective width method is a function of the reduced cross-section. Actually, when a cross-section undergoes a buckling, the part of the cross-section that buckling happens on that should be removed, and the cross-section should be analyzed based on the effective sections. And for the direct stress method, the gross cross-section can be used, and it's a function of the elastic buckling stresses and the yield stress of the material. Effective width method is most principle-based, and it's computationally expensive, and you need repeat the calculations for each buckling mode. While direct stress method, you just need to use a finite stress method that in the next slide I will explain it shortly. But what is the finite strip method? As I mentioned, in direct strength method, we need to calculate the elastic critical buckling loads. And the finite strip method helps us to calculate that actually these critical elastic buckling loads. Finite strip method breaks down the structural member into a series of narrow stripes, and then each stripe can be analyzed and to determine the critical buckling loads of that stripe. And for this finite strip method is implemented on the two software that are common in the world. The first one, which is freely available, is CFS, and the second one is Timbal 2 that was developed by the University of Sydney, and it's a little bit professional than CFS. And the other terms that are important in the direct strength method is the signature curve. Actually, the output of the finite strip method is the signature curve that is used to determine the critical buckling loads. And the pictures on the right side and the bottom of the slide is the signature curve that was obtained from the CFSM software. You can see different curves here, and each curves characterized by a buckling mode, and the lowest point is recognized as the elastic critical buckling load of that buckling mode. And the minimum of these two, actually minimum of these three, governs the design of the cross section. And the half wavelength is the other term that we need to know about it when we want to design the cold form components. And it is the distance between two successive deformed shape of the cross section. Direct strength method, or DSM, was developed based on the couple of empirical, actually experimental tests, and distinct sets of empirical equations were provided for this method. And some equations are provided for the members subjected to the compression, and the others are for the members subjected to the bending. For these ones, at the beginning, you need to calculate the critical elastic buckling loads, for example, N of OL, which is the critical buckling load of the local buckling, or NOD, which is assigned for the distortional buckling. For the calculation of these factors, you can use the finite strip method, actually CFSM or Timbal 2 software, or you can use the classical equations, or which are based on the Euler, and they are prescribed in the Appendix D of the 4600. And lastly, after calculating these three strengths, the minimum one is selected for the capacity of that member. Likewise, for the members subjected to the bending, we have another set of equations. And how about the beam column designs? In this part, I would like to explain a little bit about my PhD project. Beam column members are, primary load carrying members in the cold form steel, and they can be, they actually are common in the portal frames or the stud walls. And most of the applied loads in the cross section can provide combined actions. For example, eccentric loads that can be generated by the shifting of the cross section due to the buckling. And also we have transfer loads on the stud walls that surrounding the perimeter of the building, and also in the moment resisting cold form steel structures, we have combined actions. So the design of these elements is very important. Based on the New Zealand Design Standard and the American Iron and Steel Institute, a simplified linear interaction equation is specified for the design of beam columns. Based on this method, you need to calculate the pure strength of the cross sections for each applied load, for the compression, major axis bending and minor axis bending. So you need to use the direct strength method here. At the beginning, what I did was investigate the accuracy of the different methods in the design standards and the literature review to recognize what factors can provide the inaccuracy in the design of the beam columns. It was actually recognized that three main reasons can provide some inaccuracies in the design. The first one is errors associated with using the simplified linear interaction equation. Actually, this equation cannot capture the nonlinear behavior that we observe in our investigation. The other one is the inaccuracies of the equations for the calculation of the buckling loss, actually direct strength method. And the last one was the neglecting the effect of the warping restraint. Actually, in the common practice, the real boundary condition can provide a little bit restraint on the cross section, and the direct strength method cannot capture this restraint. For the first reason, I have provided this slide to show you how this interaction equation can provide accurate or inaccurate prediction of the strength of the beam columns. You can see the data points that are corresponding to the strength of the CFS beam columns and were obtained using the experimentally validated models against the interaction surface. And the data points were divided based on the member slenderness ratio, because during the investigation it was observed that the member slenderness ratio around the minor axis is one of the influential factors on the behavior of these elements. And also the direction of the minor axis bending can also affect significantly on the strength predictions of these elements. And for example, for the cross sections with the low slenderness ratio, the pictures on the top of the slide can show that some of the data points fall below the surface. That shows that this interaction equation in some parts can provide unsafe interaction predictions, while for other cross-sectional slenderness ratio, you can see that most of the data points are above the interaction surface. That shows that this equation may lead to the conservative strength predictions. As I mentioned, different design methods, the accuracy of the different design methods were compared in this investigation. One of the very well-known method that was recent, actually not was recently, maybe 10 years ago, was developed at the University of Johns Hopkins and now prescribed in the appendix of the new version of the AISI is the extended version of the DSM. While in the standard DSM, the actions considered as pure actions, pure comparison, or pure bending, but this method considers the true combined actions of the cross sections. The image here is from the CFSM software that can consider three applied loads on the cross section, and lastly can provide you with the critical elastic buckling load. And based on this method, the X, Y, Z coordinates, which are common in the interaction surface, shifted to another surface, which includes the azimuth angle and radial length and elevation angle. This is the conceptual strength surfaces in this method, and you can see different levels of the strengths, like buckling surface, yield surface, and plastic surface. After investigation of the different parameters, two different sets of interaction equations were developed in my PhD. The second one can provide the most accurate strength prediction. Is shown here. It's a trinomial interaction space with three different exponents, because it was observed that the direction and the magnitude of the bending is quite important. And the other two factors that was quite important in the behavior of these elements was member slenderness ratio and the web slenderness ratio. So exponents alpha, beta, and gamma that you can see here are function of the lambda and h over t and the direction of the minor axis bending. And to solve this nonlinear equation, I used the optimization algorithm because it was a multivariable equation. It was not really easy to solve using the simple methods. And these factors, alpha, beta, and gamma, were obtained using the minimizing the errors between the purpose equation and the predictions of the experimentally validated finite element models. In these two pictures, you can see the direction of the minor axis bending can provide different buckling. It can provide different stress on the cross section. When the minor axis bending is positive, you can see lips subjected to the compression, while the negative one can cause tension on the lips. This actually can cause differences in the failure modes, and the failure modes were truly investigated in my PhD. Here I just want to mention some of the design examples. 3 cross sections were selected from the project with 4 different thicknesses and 3 different lengths to cover wide range of slenderness. And the cross section was validated based on the experimental test results that were done at the University of Johns Hopkins for the development of the extended DSM, and the combined action was applied using the eccentric compression load. In this table, you can see the results. Actually, if we consider P of FE as a reference, we have the predictions of the linear interaction equation, predictions of the extended DSM, and the predictions of the nonlinear interaction equation. And you can see that actually there is a good agreement between the results of the nonlinear interaction equation and the finite element ones. Following that, I have tried to develop actually another method based on the deep learning method, which could provide the most accurate predictions of the strengths of these elements, and also the accuracy of the Eurocode was also assessed. In the next slide, you can see some of the visualizations of these methods. Here, the normalized strengths that were obtained using the different methods were plotted against the predictions of the deep learning. For example, in here, we have the predictions of the deep learning and the predictions of the linear interaction equation, and also extended DSM. We can see that the deep learning can provide the best predictions of the strengths of these elements with tightly clustered around the 1, because they are normalized based on the FE results, while extended DSM can provide most unsafe strength predictions for these structural components, especially when the slenderness of the cross-section is high. And also we have the comparison between the predictions of the nonlinear equation and the Eurocode in this slide. Nonlinear one was the other one that can provide the best algorithm compared to the deep learning, while Eurocode can provide the most conservative strength prediction of these components. If you remember, the other reason that can cause some inaccuracies was the direct strength method equations. This one actually needs lots of investigation. Maybe another PhD project can cover this inaccuracy. It was also mentioned in many previous studies. As you can see, for example, in the left side, we have the predictive curve of the DSM and the tested data points to develop this method. You can see that some of the data points are below this curve and some others are above this one. And likewise for the other tests that were done for providing the member capacity of the cross sections. And lastly, we have the effects of the warping restraint. The effects of the warping restraint was investigated based on the cross-sectional shape, and over 900 cross-sections were tested for this one. And you can see plane channel, lip channel, which we called it edge-stiffened channels, and also other channels which include sigma channel and lip channels with intermediate web stiffeners, and other different parameters that were considered in this investigation. But what is the warping? Warping restraint boundary condition. Actually, warping is a kind of distortion that can create in the cross sections when they are subjected to the torsion. If we consider just simply supported cross sections, this warping does not happen in the cross sections, while some restraining, which is really common in the practice, can provide some twisting in the cross section. So this one was also conducted based on the experimentally validated finite element models, and the cross section was restrained from moving up and down and twisting to provide this warping. And in this part of the project, the direct strength method equation was used, but to calculate the critical elastic buckling loads, two methods were taken into account. One was the finite strip method. Actually, the CFS was used, and the other one was eigenvalue buckling analysis in the abacus to predict the buckling strength of the warping restraint cross sections. And then these two capacities were compared together. And there is another well-known method that is actually specified in the appendix of the AISI, was proposed by Moen, and he, after his investigation, he developed an equation to predict the distortional buckling of the CFS cross sections when the warping is restrained. He developed his method based on shortening of the half wavelengths and multiplied the critical buckling load using the boosting factor that was shown here. Because this one is also one of the well-known methods, and the results of this investigation was compared with those obtained with the Moen's method. Again, and to compare the results, the normalized strengths of the cross sections that were determined based on the finite strip method and based on the finite element methods were compared in these figures based on the cross-sectional shape. And you can see that in all data points, we have enhanced capacity when the warping restraint is considered. The orange one corresponds to the warping restraint, and the blue one is the standard DSM. And when the intermediate web stiffeners were considered, this effect was more significant. And the factor that was important here was the ratio of the element length and the critical half-wave length of the cross-section. For the lip channels, when the length over L critical, which corresponds to the half-wave length, is over 1, no modification was required, but for the ones with lower than 1, an equation was developed here. And the green one in figure A corresponds to the developed equation, while the blue one corresponds to the predictive curve of the DSM. And another equation was developed for the cross sections with the intermediate web stiffeners, and it was observed that for all cross sections we need actually some developments to predict their capacity more accurately. And also we have a comparison in this table, and this the middle one correspond to the results of the developed equation, and you can see that developed equation reduced the errors from 13% to about 3%, and the Moen's one led to 8% errors in the strength predictions. Okay, and here I would like to mention some of the works that we are doing at HERA as an innovative in the steel structures. All work are divided in 3 main categories. First one is the structural and seismic design of steel structures, which I am more active in this part. The other one is the structural fire performance, and the last one is the sustainability and durability in steel. And for the HERA, I always try to translate what we are doing in research and what we are doing in our investigations to software design guides, to make them, to help the New Zealand engineers and fabricators, to help them to straightforward the design and also comply with the design standards. In the structural and seismic design, we have many design guides and softwares. I would like to mention two or three of them here. The most recent one was the diaphragm design in a steel frame, and also the other one is the seismic design of moment-resisting frame that will be published soon. And the other one that some of you may know is the seismic design of the eccentrically braced frames, P4001. And we also have a couple of software, including Frisk, that helps you to design the composite columns. And this software is currently updated. On the fire side, actually, HERA helps to validate the methods and translate them to the software and design guides to help the engineers to design the steel structures dependently for their inelastic behavior. One of the interesting methods that used for the slab panel method was specified in one of the HERA reports, which is R4131, and based on this method used for the larger scale structural systems, and when a structural system undergoes a fire, and the flooring system is a composite steel concrete frame flooring system, and the beams, when the heat increases, the beam starts to deform and weakens, while a slab also starts to deform and arc shape happens on the slab, and another procedure happens on the slab panel, which is called tensile membrane action. And instead of a slab depends on the beam for the tensile part, it can create enough tensile and resist the fire. For this method, we have the design standard and the slab panel method software, and the HEAT one was launched recently for the optimization of the intomethylene. For the sustainability and durability, we have a couple of design standards and the software. We have Zero Carbon program that was launched recently and helped the New Zealand steel industry to cut the carbon embodied of their project. And also we have online corrosivity map that can help engineers to determine the corrosion classification of the project. You know, our endeavor is not limited to just steel. We are quite active on the composite parts, composite steel concrete beams. We reviewed the 2327 design standard, which is one of the benchmark for the design of the composite beams. Major revision was conducted. And also we have two other software, composite beam and slab design, which is a web-based one, and the Windows-based one will be replaced soon, which is under development now. And we have ComWeapon that is used for design of the composite beam with web penetrations. And we also help engineers by providing design examples, and the design examples for the calculation of the composite beams will be published soon. And this another project that can be one of the interesting project is the review of the P4001, which was developed for the eccentric brace frames. This one is part of the Endeavour project. As part of this project, a reusable eccentrically braced frame was developed. The optimization and their environmental impacts were assessed, and some modifications will be applied to our design guide. And also, we are running a couple of training and webinar sessions. The most recent one is the training which is designed for the introduction of our recent software, and will be on Friday. It's like, you know, it's more networking, and we would like to know the other people, engineers' perspective about our project and what are their demands. We will host a webinar in late August or September in the fire design. Also, we have a seminar series on the corrosion and also steel portal frames. And lastly, I would like to express my gratitude to my PhD supervisors, Professor Charles Clifton and James Lim, and my co-supervisor, external supervisors, Professor Iman Haji Rasuliha and Mohammad Mushtabai. And if you'd like to know more about the details of my PhD project, you can see my papers, and 2 of them are under review, and the other 4 were published. And thank you. Yes? Honestly, I don't know more about fire. Just, you know, I just wanted to introduce you, provide an introduction on the fire design. My colleague is active on this part. His expertise on the fire, but please feel free to contact him. I can provide his email address. And also, if you like, you can join us on Friday.